When r is equal to 1 and the center is at 0, we have seen that the Joukowski transform z plus 1 over z is the complex potential corresponding to the velocity given by this expression. Note that when the absolute value of z is going to infinity, then u must go to 1. We see easily that this guy when also go to infinity, and therefore 1 over this guy will approach 0. So the velocity field will go to 1. And 1 is the same as 1 with real part and 0 as imaginary part. So this means that the first component, the horizontal component, is approaching 1 and the vertical component is approaching 0, which is rather naturally far away from this cylinder. Similarly, we have that this complex potential, the same as before, just multiplied with some constant a real constant, will describe the complex potential corresponding to the velocity given by the exact same expression as above, just multiplied with a. So in this case, when z is very large, we are approaching the u is approaching this number a, and in the same way we see that the horizontal component approaches a and the vertical component approaches 0. Even more generally, if we have some radius equal to a on the cylinder, a is some positive number, and we have a center at this complex number z0 with the real part x0 and y0, then we can use this complex potential. We just see that we have in the original expression we have replaced z by z minus z0, and we are multiplying with this constant a, which is the velocity in infinitely far away from the center. So this describes the complex potential, and we can find the corresponding velocity exactly as above. We obtain that the velocity is given by this expression. So we have, in the same way as above, that when you are approaching infinity, the set is approaching infinity, then the horizontal component of the velocity field goes to a, and the vertical is approaching 0. Now we can proceed exactly as for the trivial case when z0 is 0 and a is 1, by putting z equal to z0 plus r multiplied with the exponential function of I theta. So what we did in the first case, in the case when z0 was equal to 0, is that we just used this term. Now we have to add the center of the circle as well. So doing exactly as we did in that case, we obtain that the complex potential can be written in polar coordinates in this way. So here we have the real part, and here we have the imaginary part. And as before, we want to look at cases where this imaginary part is equal to some constant, because that's how we can find the streamlines. So the fact that this is a constant is equivalent with looking at this as some constant k, because this constant k is just this constant above divided with the velocity at infinity a. This gives the following equation when we have multiplied with r and divided with sine theta. We have to assume that k over 2 sine theta is larger than 0. The reason for this is that just look at this expression. The circle is centered at set 0, but the radius is a and on the circle, or the cylinder if you like. But r must be larger than this circle, because we are not interested in what's happening inside the circle. The fluid is around it. So r must be larger than this a, and this means that this must be a positive number. So we can assume that k over sine theta is larger than 1. So we can just find, this is just a second order equation. We can solve it with respect to r, and we obtain the following expression. The solution of this second order equation is, of course, two components, one with plus here and another with minus. But the minus value we can ignore, because this is just a negative value, and we do not assume negative values of r. So, well, we are now going to choose, at least from now on, we are going to choose cases where a is of this form, is described in the following way. This means that the circle is going through the point -1. Don't put so much attention to this at the moment, but it turns out to be a very interesting case, which we are going to look further on in connection with the Joukowski airfoil. Okay, then now we can just replace this r in the expression for z with this r described above. Just replace this r here, and we obtain this expression. We also, of course, replace a by this square root. So doing this, we are able now to find the streamlines. In many cases, we can model this in scientific workplace, and doing this, we find a lot of streamlines. Here is some example where the center is I'm pointing to the center here, and I have illustrated in scientific workplace several streamlines for different values of k. So for this k, the black circle here corresponds to the cylinder itself. So the cylinder itself is one streamline, and this streamline correspond to the k value, k equal to 0. This is a streamline corresponding to k equal to 0.1. This is 0.2, this is 0.3, and this is k 0.4. All the other values here are negative values of k. So here I have the value k equal to minus 0.1, and this is minus 0.2, and so on.